Good afternoon, friends. So you are back to the classroom. Today is the third lecture of Neutron as probe against matter. So we'll continue from where we left last day. So this is I will explain. I was explaining to you that neutrons have a fundamental difference with respect to other scattering techniques, especially that in case of neutrons, you find two types of scattering cross sections, coherent and incoherent scattering cross sections. Why is it so? I was explaining to you that it is because the neutron is the nucleus through strong interaction, and this neutron nucleus interaction is spin dependent. Now the nuclear spins, they are not aligned, they are orienting all dynamically. So is the neutron spin, if polarized or unpolarized, doesn't matter, but the nuclear spins are not oriented. Hence, the neutron sees a different potential when it goes from one side to another side to another side. It sees a different potential. So there is a variation in the neutron nucleus interaction potential. Unlike other, for example, X-rays, in case of X-rays, the scattering potential depends on the neutron and the atomic charge cloud interaction, and that doesn't vary from one side to another. It doesn't vary from one isotope to another. As an example, I said that if it is a nickel, if I'm scattering X-rays from nickel, the charge cloud does not change from isotope to isotope of nickel or from one side to another side of nickel, so there is no fluctuation. So because of this fluctuation, I showed you that what I showed you that I can talk about a coherent cross section B average, which is basically a average over all the sides of B. And I also talked about a fluctuation around the mean, which is B square average minus B average square. Accordingly, I told you that there are two cross sections. One is sigma coherent, which is equal to 4 pi B average square, and sigma incoherent, which is 4 pi into the fluctuation around the mean, that is B square average minus B average square. And this we can calculate for various systems. So this is the coherent part, and coherent part means this gives rise to structure, or rather this responds to the structure in a medium, or this gives rise to diffraction. This part, this doesn't have a coherent term in it. This is the fluctuation around the mean, and this is known as sigma incoherent. So today I will take up the example of how we can calculate the and incoherent scattering cross sections for a material. So first, there can be various isotopes in a medium. For example, if you take natural nickel, natural copper, they will have an isotopic distribution. If each and every isotope have a cross section of Bk and the isotopes have concentration Ck, this is a sum over the BK values of all the isotopes. And B square average is very simple. Here we are finding out for B square average, you need to square it and take a concentration weighted average. So we have B average equal to sum over K, CK, BK, where CK is the relative concentration of an isotope, and BK square, B square average is nothing but BK square, again weighted by the partial fraction of that isotope. So this is on isotopes. Now for a single isotope of spin I, if I consider the nucleus and the neutron together as a system, then the neutron has a spin half and nucleus has a spin I. So the total spin is, as mechanically, people who are from physics background, it is very easy for them. It is 2 into I total plus 1. Here I total is I plus half or I minus half. This part is basically simply to get which you know as projection operators and gives the relative weight. So when I say total is I plus half, then you have I plus half, 2 plus 1 is twice I plus 2. And when is I minus half, it is twice I. So the relative weightage are twice I plus 1 and twice I, and total is twice I plus twice I plus 1. Sorry, twice I plus 2. So I have to do average spin using these values. When I do this, when I do, if B plus is the scattering direction, the neutron spin and the nuclear spin, they are parallel. If this is B plus, then you know the weightage is twice. I made a mistake here. It should be. So total spin is twice I plus 2, and it is to be weighted. Partial weightage is 4I plus 2, because twice I plus 2 was for I plus half state and twice I was plus I minus half state. This gives you this factor, and then twice I upon 4I plus 2 gives you this factor. So B minus is when the neutron spin is antiparallel to the nucleus spin. So I have to do average over these two, and this is the weighted average so far as the spin part is concerned. I showed you the variation with respect to isotope density and now with respect to spin. Similarly, in the same way, B square average is nothing but B plus square weighted by the same factor which I explained just now, and I upon twice I plus 1 B minus square, that gives you B plus square. So now that means considering the isotope and the spin together, that means each isotope has a spin IK, concentration CK, then this is how the average goes. You have to sum over isotopes for each strength, and for each isotope for spin twice I plus half. This is the weightage, this is the scattering cross section, scattering length, I'm sorry. This is the weightage and this is the scattering length and this is the average scattering length. And this average scattering length is what gives you diffraction. I'll emphasize it again and again. And also we have this B square average, which gives you the incoherent scattering cross section. So this is the part which comes into our expression when we wrote sum over L BL average e to the power minus I Q dot RL. So far I have been discussing about with respect to X-rays, the neutron and X-ray scattering length. Now I will establish that they are also similar. So before that, I would like you to calculate using this expression the B plus or the spin. The proton is hydrogen core. I mean the proton, the spin is plus of. When the neutron spin is plus or up with respect to that, we have B plus given by 1.04 into 10 to the power minus 14 meters. And when it is negative, it is minus 4.74 10 to the power minus 14 meters. Why negative? This I will explain later. But I will request that using these values, please calculate the coherent and the incoherent scattering cross section for protons. So what you need to do is actually you need to find out, as I told you, using two values, B average and B square average, and you need to find out 4 pi B average square for sigma coherent and 4 pi B square average minus B average square for the incoherent scattering cross section. And what you get, I know what you will get, but we'll discuss it later. It's an interesting thing that hydrogen is possibly the strongest scatterer of neutrons, but it is not suitable for structure work because it is mostly an incoherent scatterer that will come out of this calculation. So now I will go ahead and I will try to establish to you that once we talk about diffraction using coherent scattering cross section of neutrons, then there is a lot of similarity between X-ray diffraction and neutron diffraction. I will show it quantitatively in this part of the lecture. So let's go ahead. The thing is that when we talk about X-ray scattering, the assumptions are I start with a plane wave e to the power I k dot r. Exactly same the way I started with neutrons, and this is my k, the incident neutron, and the outgoing neutron is again these are vectors, also a plane wave, and under Born approximation, the X-ray potential, whatever potential X-ray is offering to the system is offering to the X-ray beam, will deviate it from initial wave vector to the final wave vector. This is very, very similar to what I did earlier using Fermi-Golden rule under Born approximation. Let's go through the algebra once again. So as I said, is it changing properly? There's no sticking. No? So as I said, phi incident is e to the power I k dot r, and phi is also e to the power I k prime dot r. Under Born approximation, the scattering amplitude is given by phi scattered Vr phi incident. So this is the scattering amplitude proportional to. There are some constant factors, we keep them away. Now, if you remember, earlier also I had derived a scattering amplitude f kk prime, which is given by m by twice pi h square k prime Vr k. And if you remember, I had said that for a rigid array of atoms, the potential is given by a series of delta functions each delta function at the position where one atom is there and one nucleus is there. Now this VR, this is where the difference between X-rays and neutrons will emerge. Because in case of X-rays, the expressions are same, but the potentials are different. The neutrons see the nucleus and they interact with the nucleus and get scattered. The X-rays, usually for X-ray diffraction, we invoke Thompson scattering. So X-rays undergo a Thompson scattering by the atomic charge cloud in the medium. And this atomic charge cloud, basically the Thompson scattering, in brief, what it does actually, an electron starts oscillating under the electric field of the X-rays and emits a radiation with the same frequency. So there is no energy change. It's an elastic scattering of X-rays. When I do that, then excuse me. Now, so I need to calculate the X-ray electron density, and when I write down why it looks like this, so when I say the scattering amplitude, then K prime V K, it amounts to so, and since VR is proportional to the electron density in the medium, it comes to e to the power minus I Q dot R in R. So in brief, in X-ray scattering, the scattering amplitude is nothing but a Fourier transform of the electron density. This is a very generalized statement, I must tell you. Almost in all the diffraction experiments that we do, and I will be discussing and others will be discussing in this course, we must remember that it is the Fourier transform of some densities, and then it gives me the information in the Q space or in the angle space regarding the structure of the system. So take one from this thing, that whatever be the scattering process, I am looking at the Fourier transform of a density in real space to go to Q space. Once I say this, thank you. Then things come very intuitive and we can start discussing the Fourier transform. So as I said that in case of X-rays, electron density is responsible for scattering, which I said is a Thompson scattering. And the scattering amplitude is the Fourier transform of the scattering potential So Fourier transform is nothing but this dV is the volume of the entire crystal, n of r e to the power minus iq dot r, which gives me the scattering amplitude. Now, a few easy steps. I need to do the integration over the entire crystal. So now in this class, I'm talking about crystalline solids. So when I talk about crystalline solids, and atoms are rigidly sitting at the sides, they are comprised unit cells. So unit cells, each unit cell gives me the whole crystal. So this is what I try to show, that you can consider the crystal consisting of many unit cells. So then this integration, this is nothing but I can do an integration over the unit cell, and then I simply do an addition over all the number of unit cells, and I will get the structure factor. This I have taken, this discussion I am borrowing from Introduction to Solid State Physics by Kittel. So this is basically, many of you might have done during your master's degree. I would guess that many of you are already familiar with it, but this is my attempt to put the neutron diffraction and the X-ray diffraction on the same table. And what are the differences? What are the similarities? The Fourier transform part of a potential gives me the the structure factor in real space. That is the similarity between all scattering techniques, and so for neutrons and X-rays. Now, the next step, I said that the integration over a single unit cell, and then I can add up cell by cell for the entire crystal, and I will get the structure factor. So if I see this in a unit cell, if you see, in a unit cell, I will make a simplistic picture. In a unit cell, the atoms are sitting at specific sites. For example, if I draw this, all of you will immediately recognize this as a cubic crystal, and if I put an atom at the center, then you will recognize that this is a BCC, and maybe you can identify it with an iron lattice. So the take is that the atoms are sitting at specific sites, and they are surrounded by the charge clouds. So when I do X-ray diffraction, I can write that N of R in a unit cell is nothing but a sum of electron densities which are centered around these sites, maybe jth site inside the unit cell. So inside this unit cell, I can call this number 1, I can call this number 2, I can call this number 3, I can call this number 4, and then this nr minus rj is sum over these charge clouds, so centered around this position. So my n of r, basically n of r, which is centered around these sites. Now, I'll leave one question unanswered. In a metal, there are also free electrons, and I have considered these bound electron charge clouds which actually define a lattice point. Why I did not consider the free electron, I leave it for you to ponder over the weekend. I will come back and answer it later. So this is the bound charge cloud which is sitting at this lattice size. And this give me the charge cloud, charge density, electron density in a unit cell. So this is what I wrote here. So this is the lattice size and my n of r is basically a sum over all this lattice size what I showed you just now. So now this integration, let me do a little bit of transformations and then it will get to you which direction I'm going. So now I need to do a Fourier transform of over the charge density in a unit. Sometimes I may be missing this integral sign or sometimes I may be writing dv. Please excuse me for this random errors. When I do this, I need to say n of r equal to sum over j n r minus rj, where rj are the lattice size. When I do that, then this becomes equal to so far so good. Now let me do a small coordinate transformation. Let me write a new variable rho equal to r minus rj. Then r becomes equal to rho plus rj, right? Where rj is the lattice side and rho is the around which we are looking for the fluctuation. When I do that, then this integral this gives me the structure factor, I mean the scatter factor for my experiment. I'm sorry. When I do this transformation, this becomes and D3R, RJ are fixed lattice sites. So D3R will become D3 rho. I can now integrate over the charge cloud surrounding one particular site. So then what I get is this. Since there is no integral involved over Rj, a summation is involved, I take this outside Then I have the integral of n of rho write it more, sorry for the mess. I'll write it more clearly. There is no integration involved over Rj. Rj is the fixed lattice site around which we are doing the integration. Then the integral sign e to the power minus I q dot rho d3 rho. Okay. So now this factor, let me call it Fj. Then this becomes equal to, because these are charge cloud are jth side. This is Fj e to the power minus I q dot Rj. Now see, look at this expression. If you remember earlier, we did the same thing and I showed you f k prime k, which is similar to this one. The value was sum over j for coherent scattering cross section BL average e to the power minus I q dot RL. This is exactly same, except for this factor Fj and BL. These two expressions are exactly same. So now you see the structure factor in case of X-rays, we got this expression. In case of neutrons, we got this expression. These two expressions are very, very similar. We have BL here, which is the coherent scattering length. We have Fj here, which is an integration over the charge cloud. But this part, which dictates the diffraction, e to the power minus I dot qg or e to the power minus I q dot RL, they are exactly same. They are exactly same, similar. So this is known as a form factor for a solid. What is a form factor? So F is equal to, basically, I'll say rho or R, I'll say rho e to the power minus I q dot rho. This is what structure factor is over here. There is no integration involved here. It's a constant term. Is a big difference. And what this difference does, I will tell you shortly. There's no sticking of the, there's no complaint regarding slides getting stuck. Right. So the only difference is the form factor versus BL average. The average I missed here. And Fj, which was the form factor, is the Fourier transform of the atomic charge cloud. This is what I wrote here. Fjq is nothing but the scattering Fourier transform over this charge cloud. Now, it is the Fourier transform of the potential, or you can say the electron distribution in Q space. Now, the thing is that, interestingly, this is different between this is the big difference between X-rays and neutrons. In case of neutron, just the factor BL. In case of X-rays, you have Fj. F, which is actually a function of Q. And I can tell you to do this exercise again. Let us consider a spherical charge cloud of constant density. This is the simplest zeroth order approximation around a nucleus at the center at the jth site. So let me define the potential as n of r equal to a constant n for r less than equal to the radius of the atom and equal to 0 for r greater than r. And I can tell you that this d3r, I think I am becoming oversimplistic, but still you can try. D3r is given by r square sine theta d theta d phi dr, and this into a triple integral 0 to r minus pi to plus pi for theta and 0 to 2 pi for phi. When you do that, what you will find is this, that if you plot f as a function of q, this actually goes down like this. And if you have a larger charge cloud, then it will fall faster. This is a very simple consequence of Fourier transform. A larger object, the Fourier transform will become narrower. A smaller object, the Fourier transform will become more spread out. And in case of neutron, you find that there is no Q dependence. We just have a factor like BL. So this BL is constant over Q. What it says actually, that you have, suppose you have the same structure. You study it using X-rays, diffraction, using 1 angstrom neutrons and 1 angstrom X-rays. So you will have peaks at the same places. Intensities will be different because the scattering cross-section intensities are different. So you will find same peaks going. But in case of X-rays, you have an overriding factor of this F falling. This is pre-multiplied by this form factor. So in case of X-rays, the high order peaks, they will be killed. Whereas in case of neutrons, the higher order, the higher angle peaks, in case of X, they will be faster compared to neutrons. This is a difference. But otherwise, you should see the same structure using X-rays and neutrons if the structure is exactly same. This is one consequence. Now let us just work out the simple thing, which is again possibly known to you. But for completeness sake, so this is what the form factor I told you to calculate. As I told you just now, that when you have a larger atom, this form factor falls faster. When you have a smaller atom, the form factor will fall slowly. So for example, if you consider nickel and uranium, in case of uranium, the form factor will fall much faster compared to nickel, because uranium is a much higher, much larger size element compared to nickel. The charge cloud is much larger in volume. Now, let us do the simple selection rules for diffraction. So what does the structure factor tell us now? So now I have the, apart from I have Fj or Bj, and you have minus Now I have this structure part. I'll come. So interestingly, what does this say? Now for diffraction, we know for diffraction, this scattering vector should be equal to a reciprocal lattice vector. So that is given by, if these are the reciprocal lattice vector points, these are reciprocal lattice vectors, and Rj is a real lattice point. So I should say this will be some constant value into A, B vectors. And I have to make a dot product of these two. So, sorry. Now this is, I have come to your domain because everybody knows the basic crystallography, and what this gives is, right? This is nothing but sum of, I can say, three integers. This is what I get, and this is true for X-ray and neutron both, and this is what gives me the selection rule. So this is what I did here. So you have this, and A dot A, B dot B, C dot C, they all give 2 pi because they're the real space and the reciprocal space. And what I get here is a structure factor, which is this. They are same, only this Fj will be taken over by Bj average in case of neutrons. This has got a Q dependence. So just a simple case, let us say I have got a BCC lattice. A BCC lattice I showed you sometimes. So it has got an atom at 0, 0, 0 and an atom at half, half, half. So then as HKL is given by 1 plus minus I pi H plus K plus L, and then because half, half, half will give you half, half, half will give you H plus K plus L. That gives me, tells me if H plus K plus is odd, then e to the power minus I pi H plus K plus L goes to minus cos pi, which gives me 1, which makes it 0. Or if it is even, H plus K plus L, it will be 2F. So you know that for BCC lattice, you have H plus K plus L even reflections, and that's how we go ahead, and often we do this identification of the phase from the presence or absence of allowed peaks. These are same for X's and neutrons. The only difference is this Bj. This is where, because Bj doesn't have any Q dependence, whereas Fj, the form factor, they're equivalent, it has a Q dependence, and that makes it different. Okay, so excuse me. So now I must say that why I tend to compare X-rays and neutrons, because those of you who are already into experimental condensed matter physics, I'm sure you are reasonably well versed with X-rays, because anybody who is made a sample will first do an X-ray and then start looking for other characterization tool, X-rays, because you want to see where the phases have come out to be right, where the phase you wanted to grow has grown or not. In our case, we also will do possibly a thermal neutron diffraction to get the same structural information. Laboratory X-ray sources are quite common. Of course, we can use synchrotron based sources, and if the samples are very small, then you can go to a synchrotron with a very small quantity of sample and get the peaks. And we have two such sources, Indus 1 and Indus 2. For neutron diffraction, of course, you need to go to a reactor. A thermal neutrons are available there, and of course, we have several such diffractometers at Dhruva. At this point of our discussion, one point I need to emphasize, which is extremely important, that what we see is information in Q space, and so we are not taking photographs. So I just try to show you, if I could take a photograph of atoms in an of atoms in an FCC crystal, it would look like this. But unfortunately, we are not working in this space. We are working in Q space. We are working in Q space, and whatever information you are gathering is in Q space. So my real space structure, I have to decipher it from the information that I got in Q space. So the answer is that I can do a Fourier transformation and get N of R, but often that is not easy. Do a Fourier transform all the time. Our task is to rebuild N of R. There are ways, and actually this whole course is about that, how to use the different techniques for getting the real space structure from the structure in Q space. This is the structure in Q space, what I will get if I do a diffraction experiment. And this has to get back to this structure possibly, I don't know, once we rebuild. But this is a routine thing for X-ray and neutron diffraction people. But I must mention at this point that when I say diffraction, this is not only atomic diffraction. This whole course, we will discuss diffraction at various length scales, and various modules will attempt them to tell you that small angle neutron scattering is also a diffraction technique. Polarized neutron reflectometry is also a diffraction technique. And this case, I assume that atoms and molecules are rigidly fixed. But what about a liquid? In a liquid, the atoms and molecules, they're moving around, but even a liquid or an amorphous solid, they have got local structure. And that local structure should give us diffraction. And we do get diffraction. I will discuss it on a later lecture. Now, this is an experimental pattern. This pattern, the look of it, I would guess at least many of you will ask questions about this structure. This is not exactly what you see regularly. I'll give an answer later, not today. And I again let you ponder about it, why this structure looks like this. This is basically intensity plotted versus the Q space. Excuse me. So this is what the intensity which you map in an experiment, and Often it is not always easy to get a unique structure because they Fourier transform each other. If you could do a direct Fourier transform, it would have been easier, but often we are not able to do it. And you must be familiar with the terms like Rietveld refinement. A Rietveld refinement is nothing but you have a basic atomic structure to start with. Then you start playing with it. As you play with it, the structure changes. You take a Fourier transform of that structure and check it with the experimental value, experimental structure, find out an error function, try to minimize it, and try to say what is the true structure with respect to the structure you started with. That's why it's called a Rietveld refinement. So this we will be discussing later. Possibly not me, people who will be teaching you diffraction. And then now the time that I need to introduce you to motion. See, so far I have been talking about atoms and molecules which are fixed in space, but it is not so. They are moving. They're moving, and in case of X-rays, the X-ray moves too fast. It moves with the velocity of light. So they don't react to this motion. They don't see this motion. But in case of neutrons, it is not so. And that's a very interesting thing. So now, in the next lecture, I'll introduce you to the dynamics of systems and how we can map the dynamics also using neutrons. But today I'll stop here and I would like to summarize now. So what I attempted was actually I started with a definition of coherent and incoherent scattering for neutrons. I told you that the coherent scattering length is nothing but is the average of all the nuclear spins and all the isotopes of a system of scatterers. And incoherent scattering comes from the fluctuation around this mean. And I showed you that the coherence length that gives me the structure factor and the diffraction in the system, which gives me peaks in when I do an experiment. How we do the experiments, I'll also tell you. I'll explain you that I'll show you the experimental setups and how can do these experiments. And then I had a reasonably elaborate comparison of X-ray and neutron diffraction. I showed you that the structure factors remain same for the same structure between X-rays and neutrons. The only thing, a prefactor changes. In case of neutrons, it is the average coherent scattering length. In case of X-rays, it is something called a form factor. And actually, this form factor is also an interesting thing. I showed you that depending on the size of the atom, the form factor varies. You can ponder that if I have a system of scatterers which are reasonably isolated in space and they don't have any correlation, so there is no crystalline structure, then this form factor might give you about the idea regarding the size and shape of the scatterers. And that is the basic thing which you will be learning towards the end of this course in small angle neutron scattering. So I stop here. There is a question. I will try to answer this. Saurabh Kumar, what decides whether a nucleus will have a positive scattering length or a negative scattering length? Yes. Basically, if you see the neutron nucleus scattering system and the neutron nuclear bound system during scattering, this comes from the geometry regarding the size of the nucleus and matching of the wave function at the boundary of the nucleus. I will, if I get time, I will get into this. This basically goes in the domain of nuclear physics, but not so difficult to understand. There is a book by V.F. Turchin. I'll write it down. the book called Slow Neutrons. You might have a look at it. I can show the derivation. But it will be little time consuming. I'll try this towards the end of the talk. If I am left with some periods, I mean some hours. But this is where basically it comes from the matching the neutron wave function at the boundary for the bounds for the nucleus and the neutron inside and outside the nucleus to match it, and then I can show you that the geometry of the nucleus dictates that some small number of nuclei will negative scattering length. But for the time being, for all our lectures, I'll request you to accept this fact and then go ahead and do rest of the things. Thank you. I will wait here now. I will expect if any questions, anything, you can give your comments. I will try to answer. I will wait for some time. Please.
How does the diffraction give information of atoms or group of atoms?
A diffraction gives you information about an atom or a group of atoms because in a crystalline lattice, the position of atoms are fixed and you need to know them. I mean, if it is an NH4Cl crystal, let us say, you need to know where the NH4 ion is sitting, where the Cl ion is sitting. In an NaCl crystal, you need to know where the sodium is sitting, where the chlorine is sitting. So this gives information. The diffraction tells you what are these places where they are sitting. This is the answer for a typical solid diffraction. When you do a diffraction from a liquid, atoms and molecules are moving around. But in a liquid or in an amorphous, there are short range orders. Even in liquid, there are short range orders. I'll give an example. So these short range orders, and then this diffraction gives you the time average picture of the coordination of atoms and molecules in the system. So it basically tells you how the atoms are distributed in a system, in a crystal lattice, or in a liquid, or in an amorphous solid. That's all.
Sir? So there's a question. Am I audible?
In a trimetallic system, the speed of one metallic ion is average to the remaining two metallic ions.
1 second. What is that? Okay.
In a trimetallic system,
Trimetallic system. Okay.
the spin of one metallic ion is parallel to the remaining two metallic ions, and these two ions are itself anti-parallel. How they spins calculate?
Really speaking, the question is not very clear to me. I would request you to frame it properly. You can put it to the email address neutroncourse@gmail.com. I'll try to answer it. Is it? Okay, so I think we are done for the day. So I wish you a nice weekend, coming weekend. Stay safe during this pandemic time, but do enjoy while staying safe. And we'll meet again on Monday at 3 o'clock. Please remember, now all the talks will be at 15 hours, except for 21st of this month, when again we'll meet in the morning. I'll give you the timings later. I'll always update you, but 99% of the talks will be from 3 o'clock in the afternoon. So goodbye.